Right, so when we looked at Ramsey numbers in the context of the regularity lemma, we started by observing that Ramsey's simplest theorem says that if you have a large complete graph, large enough complete graph Kn, you can find on any two edge coloring of that complete graph a monochromatic Kr for any size R that you may have wished for. So given any R, there exists an N, and so on. And then I asked, well, how about wanting not a complete graph Kr as a subgraph, monochromatic subgraph, but any particular given graph H? Does that change the problem? And the first answer is, well, the existence problem trivially follows, because if you have a complete graph that is monochromatic, then that contains your given subgraph, provided it has enough vertices. And we made it non-trivial by then saying, but maybe the n can be reduced, and we can make do with a smaller n. So that's how Ramsey numbers came into play, and so on. Another way to make the question non-trivial for a given graph H that you want as a monochromatic subgraph rather than a complete graph is to ask for H to be induced. Okay. And a third way of making it non-trivial is to ask for this H to be contained in some graph G whose edges you color with two colors, and you want H as a subgraph, not necessarily induced, but you want G to have no cliques bigger than the cliques in H. Right? So if you apply the standard Ramsey theorem to get your monochromatic H, then you do that by choosing n big enough so that Kn contains a monochromatic Kr, where R is the order of H, but then, of course, that Kr is a clique, and Kn is also a clique, so the clique number of this G is much, much bigger than that of H. And both these ways of making Ramsey's theorem for particular graphs H rather than complete graphs more interesting have a common answer, and that is a theorem I'm going to show you today. It's the corner theorem, I think is fair to say, for induced Ramsey theory for graphs. And it says the following. It says that for every graph H, there exists a big graph G, which we call a Ramsey graph for H, with the property that when we two-edge color G, we find a monochromatic induced copy of H in there. Okay? So the existence of such a graph G, given our favorite little graph H, is not trivial. Right? We have an H, anything, Peterson graph, whatever you like. And then we want to find a G, and we'll have to work pretty hard constructing such a G later today. We want a G with a property that when we two-edge color that G, we can find an induced copy of H using just edges of one color. So the flavor of that problem is very different from the flavor of Ramsey's simplest theorem. We don't just have to ask for G to be, or take any G that's big enough and then hope for the best, as we do in Ramsey's theorem. Just choose n big enough and then start proving it and you'll succeed. But we'll have to construct this G very carefully, depending on the structure of H. And the existence theorem here says that such a G given H does indeed always exist, and the one we'll be constructing has the additional property that it doesn't have any cliques bigger than those in H. So its clique number is only that of H. It can't be lower because it will have to contain H in one color, but it won't have any bigger cliques than that. So both these answers that are these ways of making the simplest Ramsey theorem more interesting for graphs H other than complete graphs KR have a common answer in this theorem. Okay. For the proof, we'll need two lemmas. We'll approach this slowly. And the first is to show that every bipartite graph has a Ramsey graph. So if H is bipartite, we call it P. And then we'll show that there is a Ramsey graph for this P. That's going to be the second lemma. The first lemma just gives us a way of standardizing P. The first lemma says that any bipartite graph can be embedded as an induced subgraph in another bipartite graph that has a particular form. And the form is that its first partition class is anything, call it X, and then the second partition class has a particular form. It consists of all the K subsets, exactly K vertices of X. And it has edges that are precisely prescribed as well, namely all those edges xy such that X is a subset, an element of Y. Okay? So these are the K subsets of X. And for every little x, you can ask, is my little x contained in that K subset or not? And if it is, we make the little x adjacent to that K subset. So the picture is like this. Left-hand side is x, right-hand side has as elements y, that's an element of the right-hand side, and I denote it by big Y because it's, in fact, a K subset of X. Right? So x1, x2, x3 are going to be the neighbors of that set, x1, x2, x3 for k equals 3. Okay, that's just one very particular type of bipartite graph, and the first lemma says that any bipartite graph can be embedded in one of those. And by embedded, I mean embedded as an induced subgraph with the additional property that the left-hand side is embedded in the left-hand side and the right-hand side is embedded in the right-hand side. Okay? That notion of embedding I shall be using for bipartite graphs throughout today. So I may forget to say it later, but that's what we mean by embedding bipartite graphs. Okay. So let's prove that lemma. So given any bipartite graph AB with some edges, find a P prime of that form such that P is an induced subgraph of P prime respecting classes left to left, right to right. Okay, so how shall we do that? Here's our little A. Let's say that A has 5 vertices. And some neighbors. So maybe this one. Okay, I managed only 4 vertices. Never mind. So maybe this neighbor here, little b, is adjacent to those 3 out of the 4 vertices in H. And there are other b's as well. This is P. Let's try to think of P prime of this particular form where we can embed this. Well, we want the neighbors of these this neighbor of the 3 vertices to become a K-set of vertices of the left-hand side. So the left-hand side is going to be some x, because we want a bipartite graph P prime of this form. And we should want to embed all the vertices of A somewhere there. Okay, and this B will have to be a K set for some K to be found. That should be adjacent to the corresponding images. Let me write it like this. Right. So this is going to be whatever 5b. That's a vertex on the right. Every vertex on the right is going to be a K subset of X. Okay, what subset of X could we choose? Well, it has to have the right adjacencies, so it should only be adjacent to these 3 vertices, not to that one, because we want P to be induced in P prime. And some vertices in B may have many neighbors in A, and some have few neighbors in A, maybe some have no neighbors in A. But the images of those vertices in B must also always be K subsets of this X. So they always have to be sets of the same cardinality K. Okay, so we can't just let phi of B be the set that consists of those neighbors, because then these sets would differ in cardinality depending on the vertex in little b and on how many neighbors that has in A. But what we could do is put those 3 neighbors in this set and a dummy vertex. so that this information records that amongst the images of A, it has precisely these two neighbors, as it should, being an image of little b. Okay, so this dummy vertex has to be in X as well. So we put it there. And how many dummy vertices do we need? Well, we need up to 4 dummy vertices, up to whatever cardinality A dummy vertices, because it might be that some vertex in B has no neighbors. So its image will consist of dummy vertices only. They all have to be in X. Okay. So that would be a good plan, right? That's my tentative definition of P prime. Left-hand side has twice as many vertices as A does. The first half is designated as images of A. The second half is equally many dummy vertices and a vertex of B to the subset of size cardinality A in here. So K would be cardinality A that consists of the neighbors of the B whose image it is under this embedding, plus for every non-neighbor, one dummy vertex. Doesn't matter which. So, okay. Does that do it? Almost. There's one tiny little problem, and the tiny little problem is that we could have another vertex here that has the same neighbors as B. Right, then we would want this to have the same form. So plus a dummy vertex. And now we're getting into trouble because we must not choose the same element, the same K subset of X, because then this would be the same vertex on the right. Okay, maybe you think we might get away with choosing these dummy vertices differently? Yeah, but we don't really, we can't assume that there are enough of them, right? Because B might be much, much larger than A. So let's be generous and add lots of further dummy vertices, as many as B has elements. And then add such a vertex to every K set on the right. And we now redefine K as not order A subsets of X, but order A plus 1. Yes, plus 1, where these order A subsets are defined as before, and we always add one new dummy vertex just as a tag to say this is the 17th little b. Right? How many tags do we need? One for every vertex here that we embed there. They all get different tags, so they can happily have the same neighbors, They can be adjacent to the same images of vertices in A. They can even be adjacent to the same dummy vertices that we originally had to fill these sets for non-neighbors of little b's because they'll have their special further vertex that only this particular set has for every image, for every little b in big B. Its image will have a special vertex, namely that, the one here from the additional ones, that corresponds to that little b in its image. And that's the proof. So that's it. Questions? No. Okay. Right, so if that's clear now, then I'll proceed to the second lemma. And the second lemma now says that every bipartite graph has a Ramsey graph. And now, of course, since we have our first lemma, it's enough to prove the second lemma for bipartite graphs that already have this special form, right? Because if we have an arbitrary bipartite graph and we want a Ramsey graph for that, we first embedded in the graph of this particular form in an induced way, respecting the classes. And then we'll find a Ramsey graph for that. So that's going to be another bipartite graph, every two edge coloring of which contains a monochromatic copy of this bigger graph than our given graph. But then that bigger graph contains our given graph, so we have a monochromatic copy of our given bipartite graph as well. We'll embed a given bipartite graph, P, in some other graph of that same type, P prime, P prime is going to be X prime K prime subsets of X prime and edges defined in the usual way, with a property that for every edge two edge coloring of this, we shall find a monochromatic induced copy respecting classes of this in there. Okay, and this page already gives away what K prime is. I didn't intend to give it away just yet, but there you go. It's 2K minus 1. But I'm not going to tell you what X prime is. Well, X prime is any set. The only thing to tell about a set is how big it is. And we'll see that much more later. So once you know how big X prime is, you know this graph, now that you know what K prime is. Right? K is given, along with P. K prime is going to be 2K minus 1. And then this graph is completely determined once I've told you how big X prime is. I'm not going to tell you because it'll just be completely confusing. We'll just work on the assumption that x prime is big enough, or as big as we need it, and then see what happens. And then eventually we'll see how big we need x prime to be. But once that size is fixed, this graph is completely determined up to isomorphism of bipartite graphs respecting classes. Okay. So let's begin our mock proof of this lemma just with this p prime specified, nearly specified as up there. Okay, so the mock proof says, well, let a two-edge coloring of p prime be given. Let two-edge coloring of p prime be given, and let's find in it a monochromatic copy of p, induced copy of p. Okay. So we'll have some x prime, and we'll have the set of all k prime subsets of x prime as vertices on the right here, and I'm drawing these vertices as subsets of x prime, or maybe not. Maybe just for once, let's draw a vertex as a vertex. So such a vertex will have some neighbors on the left. Say those neighbors here, and not the others. Well, those edges have been colored, red and green. So some of these edges are green, and other edges are red. All in all, how many edges are there? How many edges are there? What's the degree of a vertex on the right? Yes, 2k minus 1. Right? It's a k prime subset of x prime, and it's adjacent to its elements. Right? So it has degree k prime. 2k minus 1. Okay. So out of these 2k minus 1, some k will have the same color. So let's call this vertex big Y, right? Big Y is a k prime subset of x prime. And we, for every y in the right-hand side of p prime, for every vertex y on the right-hand side is for every k prime subset of x prime, choose, well, let's call it y prime, because it's a subset of x prime. For every such y prime, choose a subset z prime such that all y prime x prime edges with x prime in z prime have same color, green or red, right? So here, this subset here of x prime would be y prime, that vertex, and that would be z prime, and the color will be green. All right, we can do that for every vertex on the right-hand side, which is a k prime subset on the left. Remember, for every k prime subset of x prime, its special subset z prime, and the color of its edges to z prime. So for this particular y prime, we remember its first three elements as z prime and the color green. Right, and now the vague hope is somehow to find, if x prime is big enough, some subset in there to map the elements of x to. We want to embed pi in pi prime, right? So we have to map the elements of x to elements of x prime. To choose as the image of big X some carefully chosen subset of x prime with a property that somehow all these edges to that subset have the same color, either all green or all red. Because in that case, we would have a monochromatic copy, green or red, of P and P prime with, once we have mapped these vertices, the vertices in X to vertices in X prime, we'll still have to map the K sets of X to K prime subsets of X prime, which may contain some of those images of X, but maybe some other vertices as well, like the dummy vertices earlier, and so on. So that will have to be defined still. And the vague hope is somehow to, choose the images of big X and these images as vertices on the right-hand side, K prime subsets on the left, carefully so that they somehow conspire that all these edges are green or all these edges are red. Okay, so now you go away for 3 weeks and you think really hard about it, and then you come back with the following solution. This proof is due to Rödel, and I think he did it in his master's thesis, so at your level. Rödel was Matthias Schacht's supervisor, and he still comes and visits once a year or something. Okay. Next, we remember a little more, and this is a clever bit now, we remember a little more for every y prime, that's a vertex on the right, than its subset z prime and the color. let's say, y prime is a 5 subset, and the edges, can you see that as green or is it white for you? You can see it as green. Okay, so it's subset Z has 3 elements, 3 out of 5. So the others were red edges. Okay. And this Z has the position 1, 3, 4. In y prime. Yeah. In y prime. And that's a 5 set. Right? 1, 3, 4 are not the names of these vertices here. They're the positions. So let's enumerate the vertices of x prime once and for all. So there's one linear ordering. You always have a smallest, a second smallest, a third smallest, and so on. And then you can remember for any subset of a k prime set in x prime, and those subsets are going to be the vertices on the right. For every such k prime subset on the left, you can remember the positions of the special subset z prime of that we chose. Okay, how many positions are there? There are k prime, choose k, many possible positions. Of z prime in its y prime. Right, there are lots and lots and lots of vertices on the right. Each one of them is a k prime subset of x prime. Each one of them has its special z prime in it, sitting in a particular way. And we encode the position of its subset z prime of k prime. K prime, I don't know, are the natural numbers from 0 to k prime minus 1? Right, so k prime many natural numbers. And a position is a k subset of that set. Okay, so the reason I'm sort of making this so formal is that it's important that positions are something that all these k subsets, k prime subsets of x prime that appear as vertices on the right have. They all have the same position, the same kinds of positions. All these positions are k subsets of the integers between 0 and k prime minus 1. So we can compare them. We can say that 2 of these vertices have the same position of their z prime in them. Okay, and that's where Ramsey kicks in. So we color color the K prime subsets Y prime of X prime, so those subsets that are vertices on the right, color them with the pairs possession of their Z prime in them, comma, color. Red, green for the edges from it to Z prime. All right, so these are pairs. They're K prime, choose K possible entries here. There are two possible entries here. So there are twice K prime, choose K possible colors for the subsets, the K prime subsets of X prime. And now, Ramsey's theorem finds us monochromatic subsets of X prime that's as big as we want, provided X prime is as big as we want. And we've reserved our definition of the size for X prime for precisely this purpose. So how big do we want this W to be? K times X. Yeah. Order X plus K minus 1. Okay, so assume that this theorem gives you the existence of such a subset W of X prime, that big, that is monochromatic. Do you remember the definition in this, or do you remember the Ramsey theorem for K sets rather than edges and many colors at all? No? Okay, then, whoops. So the Ramsey number of K, C, R is the minimum size n of a set that will ensure the following. You have a big set, n elements, n being this number at least. Big set. All its A subsets have color, one of 17 colors. And then there exists a subset of that big set, big N set, of size at least little r. Little r is what we wished for, but had to pay for by this N becoming really big. Then it has a subset of size at least r, with a property that the K subsets of that R subset all have the same color. That's the only way in which it makes sense to say that an R subset of the big N set is monochromatic. Because what carries colors? The K subsets carry colors, not the vertices, not the elements of that set. So the subset, the R subset of this big N set is monochromatic in the only sense that is possible, namely that its K subsets all have the same color. Right, and now we do that here it's going to be the Ramsey number of k prime. How many colors do we have? Twice k prime choose k. Remember? Those are the colors. Twice k prime choose k colors. We're coloring the k prime subsets of x prime, those that are vertices on the right. So that we can find a monochromatic subset of the size that we want, and this is the size that we want. So now I've told you the precise graph P prime. I've told you how big x prime is, and then everything else is fixed. Now all I need to do still is to persuade you that we can embed P in it so that the edges that the image of P uses are all green or are all red. So this was P. This is P prime. P had 5 elements. Sorry, X had 5 elements in our example. And we'll have to map those to X prime first. Let me draw these. A little spaced out, and we'll have some dummy vertices. So k is 5. We have k minus 1 dummy vertices between any two blue vertices. Those are going to be the image of x. And I'll be working only inside this special subset W that Ramsey gave us, subset of x prime. And remember, the size of that subset was k times order x plus k minus 1. So for every vertex in x, we have its image and k minus 1 following vertices. So that's k times k vertices for that particular blue vertex in x. For the second, we also have k vertices. For the third, we have k vertices. Always its image and then k minus 1 dummy vertices, all the way up to down there. And then we'll have k minus 1 extra dummy vertices at the top. Okay, and now I want to embed y, a little vertex on the right here, big letter y because it's a k subset of x. And the k subset I want is those. Okay, let it be adjacent to x1, x2, and x4. So k is 5. And now we want an image of that. Here. What's the image going to be? The image is going to be a k prime subset of W. And now I think, yeah, now I want to write it as a set, at long last. So this is going to be phi of this vertex y It's going to be a K prime subset, not anywhere in X prime, but of W. And we want it to be adjacent to certain blue vertices here, namely to the images of x1, x2, and x4. X1, X2, and X4. And we do not want it to be adjacent to X3 and X5. Right? We want an induced embedding. So how can we engineer this? So we're free to form a K prime subset of W here. So we can add a few more vertices. And the vertices we want to add will be such that the adjacencies between y prime and these blue ones turn out to be green edges. If green was the color returned by Ramsey here. So assume Ramsey returned green and position 1, 3, 4. Right, remember that was a color. A pair between a position and green-red was a color, and all the K prime subsets of W have the same color. Okay, so now we want this y prime to have its neighbors, or to have the vertices on the left to which it should be adjacent in this position where we know that all the edges are going to be green. And which position is that? Well, 1, 3, 4. So we want this to be the first vertex, that to be the third vertex, so we need a dummy vertex here. 3, 4, and we need another dummy vertex here. So that's going to be our choice for the vertex on the right here, to which we send this vertex big Y, K set in X. Yeah. Then all I can say is that works. Yeah, so why does it work? We embed all these blue vertices to these blue vertices here. We embed the vertices on the right to K prime subsets of this W like here, and then we want the edges here to be all the same color. Color is going to be the color chosen by Ramsey. It's going to be green. And we know that all these K prime subsets of W, they have the same Z, they have their Z prime lying in the same position, namely in the position 1, 3, 4. In this case, right? So we want to make the vertices of that K subset that's going to be the image of this, that sit in position 1, 3, 4, adjacent to these, to the intended neighbors, namely the images of its neighbors, the Y's neighbors here. And we can do that by adding the dummy vertices that we need to fill up to form a K prime subset of W as a vertex on the right by filling in those padding vertices so that the correct neighbors lie in the desired position 1, 3, 4. Yeah, and so they're all green, and we have embedded P and P prime, and it's induced. Questions? Yeah. Sorry.
The positioning on X is 1, 2, 4, right?
Yes. Yeah. No. No, that's nothing to do with the position. These happen to be the neighbors of this vertex on the right, on the vertex on the left. The position that we remembered for the intended Z, for the Z prime in the intended Y prime to be the image of that is going to be 1, 3, 4 because the Ramsey application told us that. So we need this Y that sees, that's precisely why I did not draw 1, 3, 4 here. So this Y has neighbors x1, x2, x4, but we want these to appear not in position 1, 2, 4, but in position 1, 3, 4. Right? Yeah. Okay, yeah, but absolutely, that's exactly the one sticking point here to understand. Yeah. Mm-hmm. Other questions? Okay, then we have this lemma, and now we're going to prove the theorem. And that's really cool. We make a big construction, absolutely breathtakingly big, in very simple steps that are conceptually quite simple. It's mind-bogglingly big, but it's quite easy to understand once you have it. The lemma was more difficult than the main proof. So, once more, given any graph H, we want to construct a big graph G with a property that for any two edge coloring of G, we can find a monochromatic induced copy of H. Okay, so we'll be constructing graphs G0, G1, always embedded in bigger graphs, all the way up to Gm. I'm going to tell you what M is in a moment. And the last one, Gm, is going to be our Ramsey graph G for H. Right, and now I'm going to tell you what G0 is. Let N be the Ramsey number of R. Very simple. So N is the minimum integer N, such that when we two-color the edges of Kn, we'll find a monochromatic Kr in it. Okay, and think of I'm going to write something like a matrix here. And it'll have height n, right? And we'll have columns one for every way of sending R vertices to an N set. There are many ways of sending an R set to the same image here. We could permute all these vertices of H, but we don't do that. We just choose one embedding of the vertices of H in this N set. And the idea is that already here, this is beginning to emerge. It'll be more complicated later. This is a graph. At this time, that will change. At this time, the edges are all vertical. They stay within the same column. We shall embed this graph G0 in a much, much bigger graph Gm, by inflating the pairs of rows. So if you pick a row I and a row I prime, there's some edges between these rows. That's a bipartite graph. And we're going to blow up this bipartite graph, P, to a bigger bipartite graph, P prime, that comes from the lemma for P. Right? It's Ramsey graph, P prime. We do that for these two columns, then we do it for rows, then we do it for another two rows, and so on. And we always make this graph, we'll adjust this graph at every step so that not only these two specified rows get expanded to a much bigger bipartite graph, but the other rows are sort of copied along so that the entire graph G0 becomes a subgraph of G1 with these special two rows mapping to two rows, the corresponding two rows of G1, which are then going to be the P prime. And the other rows of G0 are just going to be copied to G1, and I'll show you how in a moment. And so on. And the idea is to do that in such a way that when we two-edge color G, then this will contain a copy of G0. It will contain a copy of Gm-1, and that will contain a copy of Gm-2, and so on. And all the way down to G0, this G, on having its edges two-colored, will contain a copy of G0 that isn't quite monochromatic, but edges between the same two rows always have the same color. So all edges between row 1 and 3 are red, all edges between row 1 and 5 are blue, and so on. 2 and 5, whatever. Right, so once more, I'm promising you that this tower of embeddings will be such that when we, at the end of the day, two-edge color G, we'll find in it a copy of G0 whose edges between a fixed pair of rows all have the same color. And remember, through this expansion, the rows remain identifiable. So there's always going to be n rows in each of the graphs, including G at the end. G will also have n rows. Okay, and once we have found such a copy of G0 with the edge color only depending on the pair, we contract every row. What will that give us? That will give us a graph on the set n, right? All these edges between the rows 1 and 2 will be copied to the contracted vertex 1 and the contracted vertex 2. And since they all have the same color, if there was at least one edge, that would give us, say, a blue color between 1 and 2, and so on. And that will give us a two-edge coloring of Kn. The edge coloring of Kn, by the choice of n, will have a monochromatic Kr in it. Right. This R corresponds to a row here. Now we undo the contraction. And we'll find that for this particular R, say here, all the edges have the same color. All the edges have the same color. In particular, all those of this H in there. And that is going to be our monochromatic copy of H in G. That's the plan. And now I have to show you how to blow up these pairs of rows that are bipartite graphs P to bigger bipartite graphs P prime, and to carry all the rows along to the next level. So for the induction step, where we assume we have defined GK, and want to define, or the recursion step, we want to define K GK plus 1, so K let's do that now. So we'll have lots of rows. And row, say, I1 and I2 are that one pair of rows we're targeting now. And we'll target every pair of rows once, and that's what this little m is. The little m is the number of edges that Kn has, right? It's n choose 2. N choose 2, one for every pair. Okay, and on this pair, there sits a certain, oh well, I can use white. Graph, just induced by these two rows in GK. So all I'm promising is that GK has rows that come from these rows, right? N many rows. We're looking at two of them, and they span a bipartite graph. We call that P. And these rows are going to be expanded to sets that we'll call W1 and W2. And those come from P that consists of I1 and I2 at time k, that's P. And from its embedding using the earlier lemma into a set P prime, into a bipartite graph P prime, with classes W1 and W2. So at the start in G0, all the edges were vertical. That's no longer the case now. That'll survive probably only one step. Right? And now the edges can crisscross, but will never have horizontal edges. always edges between different rows. And these rows, V, VI, they will grow. They'll massively explode. With every step, they'll grow really, really a lot. As you can see here, so these particular rows form the graph P, and remember that P prime is much, much bigger. It has as X prime some Ramsey number of, right? So at the next level in G k plus 1, the rows I1 and I2 will be these classes here. That will be vastly bigger than at level K. And now the task is to extend this embedding between just the bipartite graphs to an entire embedding from gk to gk plus 1. We already know what to do with these two rows, but we have the other rows as well, and they send edges to these particular rows. And those other rows have to be carried over to gk plus 1 as well. The naive way to do that would be to just copy over the other rows. Right, so this is a row here, VI, say. And, well, we could say this vertex here has some neighbors in there. Maybe they're also adjacent to other vertices up there. And we could just say, okay, these vertices now become vertices in P prime because P gets embedded in P prime. So we could make these image vertices in P prime adjacent to those neighbors as well. There's a problem with that. And the problem is that such a vertex here, when it's sent to P prime, the image, this, could be the image of other vertices than this one, its image. This is a little v. That becomes a v prime here under any embedding of P and P prime as an induced subgraph, which is why we invented P prime in the first place. The reason we're using these P primes, what are they good for? They have the property that when we have a two-edge coloring of P prime, we can find a monochromatic P in there. Okay? And we want this monochromatic embedding to somehow extend to an embedding of GK in GK plus 1. And this is where the problem arises, because this V is sent to some V prime under some embedding of P and P prime. Embeddings of P and P prime might send a different little u to the same V prime. And we don't know yet which is going to be the monochromatic embedding that we'll want at the end of the day. We'll have to somehow cater for every possible embedding of P and P prime as the potentially monochromatic one. And some Ramsey set, some edge coloring that's given to us at the end of the day of G will ultimately tell us which is the right embedding. So, since we don't know the embedding, we can't copy these adjacencies to GK plus 1 because the image of V, this little V prime, will then become adjacent to, or will also be the image of other little u's than this one, and some of them may be adjacent to that vertex, and others may not be adjacent to that vertex. So we can't copy the adjacencies and hope that GK will be induced subgraph of GK k plus 1, which we do want. That's why we don't just copy the layers across, but we do nearly that. Namely, for every possible embedding, we choose a copy of rho vi. So let phi 1 to phi q be the embeddings P and P prime, right? Q many. And the vertex set of G k plus 1 is going to be what? In row I and I1 and I2, the vertices of P prime. In any other row, I, Q, little q many copies of this row, Vi, k. So Vi k plus 1 is going to be q copies of Vi, all different. We know how to embed P and P prime. That is some convoluted way, but maintaining rows by our definition of induced embedding between bipartite graphs. Maintaining rows, but otherwise something strange. Now we have the other, we have rho Vi, and rho Vi has q copies of it in G k plus 1. For every p from 1 to q, we have one embedding of gk and gk plus 1. Right? For every way of embedding these two rows, call it little p, we can extend that embedding to an embedding of gk and gk plus 1 by just keeping this little p as the index that tells us which copy of the ith row to use for other i's. So what does this gk plus 1 look like? For all the levels I, other than I1 and I2, it has q flat copies of Vi up k. They're all sitting there, right? And here, these copies are not as disjoint, but they're lumped together to form P prime. And then the edges are just what you think. So the edges of gk plus 1, once more, we let little p run through its index set from 1 to q, and then we'll add all the edges between the vertices that are copies in gk plus 1 with respect to that index little p of two vertices of gk. So for example, if you have this edge here, that's a vertex, a special vertex that will end up somewhere in W1. This is a non-special vertex that will be mapped to its copy, one of its q many copies. Now we're fixing a little p, the index, so that gets mapped to the pth copy of it at level I. And this edge corresponds to that choice of little p. So we have an embedding of gk in gk plus 1 for every little p that is an embedding. We extend these embeddings to embeddings of the entire gk and the entire gk plus 1. Yeah. And notice that for every 2 edge coloring of gk plus 1, there is a key gk in it whose edges between W1 and W2 all have the same color, namely the one that corresponds to P. So once more, take a two-edge coloring of GK plus 1. That is a two-edge coloring in particular of this bipartite graph P prime between the corresponding rows. That has sitting in it a monochromatic copy of P. Take that P, that is a particular that is embedded in a particular way in this P prime, so that it becomes monochromatic in there. This particular way has a name, that's a little p. Use that little p to embed the rest of GK there. Then we have an embedding of GK plus 1, that is monochromatic on this pair. And now we're there. Now we do that starting right at the end. Once we've done all the pairs, we'll take a two-coloring of this, of the last one. Find in it, in this GM, a copy of GM minus 1, in which all the edges in the last pair are monochromatic, are the same color. From then on, only work with this particular copy of GM minus 1. That also has a two-edge coloring inherited from the two-edge coloring of this. Then look at the next pair. This copy of GM minus 1, which has a two-edge coloring, and the edges in the mth pair are already the same color, has a copy of GM minus 2 in it, in which all the edges between the second pair of rows that were, or the second last pair of rows, are also the same color. From then on, only work with that copy. And then it has a copy in GM minus 3, where the edges between the third last pair of rows is monochromatic, and so on, all the way down to G0. And in G0, I told you that it will have the property that it'll be a copy, it will have an induced embedding in G that we two-edge colored at the start, with a property that the color of its edges will depend only on the pair of rows. And that's the end of the proof. Is that magic? Now, it's all very well to sort of read it and then say, yeah, that works. But imagine finding that. I think that's really, really brilliant.